So I'd like to thank the organizers for the invitation to be here. It's really a pleasure and an honor to speak in this special session. So I'm going to describe some work in progress with Anfried, this guy here, who you just saw, but I think now he's mercifully escaped before this. So, it only works when I'm close. Okay. All right, so what is this about? So this is going to be about Abelianization in classical Chern-Simons theory. What do I mean by that? I mean a relation between two different Chern-Simons. So on the one hand, the classical GLN Chern-Simons theory on a manifold, which I'll call M, and the GL1 Chern-Simons on a covering, an n-to-1 covering of M. Except that there'll be one slight modification. So the GLN Chern-Simons are just the ordinary Chern-Simons that we know and love. The GL1 Chern-Simons is going to be slightly modified by the addition of some kind of additional defects. Okay. So, and the idea is somehow going to be that this is going to be a good way of thinking about the GLN theory. So the GLN theory you think of as being somehow complicated. It involves this non-abelian group. In practice, if you want to say calculate a Chern-Simons invariant, that's somehow a complicated thing to do. On the other hand, the GL1 theory is, in some sense, almost trivial. And so reducing from GLN to GL1 is supposed to be a big simplification. So what I'm going to describe in detail is a kind of classical version of a proposal that's been around for a while. In fact, it was proposed by Jacobi, Cordova, and Baffa that even the quantum Chern-Simons should be identified. We're not in a position to be able to prove that, but we are in a position to make a pretty precise version of the classical story, so that's what I want to explain. And this proposal is also pretty close to a circle of ideas around quantum field theories of class R. I'm not going to say a lot about that relation today, but it's certainly kind of there in the background. Another thing I should say, unfortunately, we realized at some point that Abelianization of Chern-Simons is somehow not a good name because, first of all, there are many things called Abelianization, and second of all, specifically, there was already something called Abelianization of Chern-Simons, studied by Beasley-Witten and a related thing by Blau-Thompson. And I just want to say that this, what I'm going to describe, is not the same as that. Okay. So let me quickly remind you what I'm going to talk about. So what is the GLN Chern-Simons invariant? So, okay, so suppose you have a compact spin-3 manifold with a GLN connection. Then there's a number, which is called the classical GLNC Chern-Simons invariant, or the Chern-Simons action. And concretely, if your connection is on a trivial bundle so that you can write it kind of D plus A, then it's literally given by the standard formula for the Chern-Simons action. Here it is. So that's the quantity we're talking about. And I'm going to focus mostly on the invariant for, well, I think entirely on the invariant for flat connections. So in other words, I'm just going to look at the critical points of this action. I'm going to ask, how can you calculate that invariant? Now, there's a little generalization of computing the invariant for closed 3 manifold, which is to study a manifold with boundary. And if you study a manifold with boundary, there's still a perfectly good notion of the classical Chern-Simons action, but it's just not a number anymore, because the integral that you write down is not gauge invariant. It's gauge invariant on a compact manifold, but to see that, you have to use integration by parts. Without the integration by parts, it's not gauge invariant. What you can say instead, it's not a number, but it's an element of some canonically defined line, a one-dimensional vector space. That one-dimensional vector space is just determined by the restriction of your connection to the boundary. So the Chern-Simons invariant is an element of this line associated to the boundary, and you could think of this as being kind of the Chern-Simons invariant of the boundary, this one-dimensional vector space. And a little more generally, if we focus for a minute just on the boundary, now don't think so much about the bulk, think about the boundary. For every possible flat connection over the boundary, there's a line there. It's the place where the bulk invariant would live. So we have one line for every flat connection over that boundary, and those fit together into something called the Chern-Simons line bundle. So there's some naturally defined line bundle over the moduli space of flat connections, which just comes to you from Chern-Simons. Okay? So what I just said might sound a little bit like the structure of topological field theory, And it is an example of a topological field theory. Just to say the precise words, it's a three-dimensional invertible. Invertible because here the invariant is not just a number, but a non-zero number. The vector space is a one-dimensional vector space, and so on if you go lower down. So it's a three-dimensional invertible spin topological field theory with GLNC symmetry. So saying that it's with GLNC symmetry means that we don't just take a manifold, we take a manifold with a GLNC connection. So this is actually an example of, we say all the time that Chern-Simons theory, where you integrate over connections, gives you a topological field theory. But even the classical Chern-Simons theory is also a kind of topological field theory, where you couple to a background GLNC connection. Okay, so the statement that I want to say is really not only a statement about the three-manifold part, it's a statement about the, well, in principle it should be a statement about the whole theory. Today I'll focus just on the 3-2 part. So the lines and the elements of those lines. Okay, and now before I turn to the Abelianization, the GL1 theory, let me just recall one sort of interesting fact about Chern-Simons on closed three-manifolds. So suppose that we consider a manifold which is triangulated, or let's say ideally triangulated. So that means we get it by taking some bunch of tetrahedra, gluing them together along the faces in some way, and then deleting the vertices. So deleting those vertices creates some boundary, but that boundary is not a big deal for us. We'll consider connections that are kind of trivialized at the boundary. So you may as well forget that that boundary is there. So this is essentially like taking a closed three-manifold. So this particular example, here's these two tetrahedra. If you glue them together by the pattern on the edges that's shown here, you'll get a three-manifold, which is the complement of the figure 8 knot. Famous example. So suppose you have a three-manifold like that comes to you triangulated. Then there's a construction of flat connections over such a three-manifold, which comes to you by you do something local in each tetrahedron and then you glue them together. And the data that you need in order to construct the connection is a bunch of numbers in each tetrahedron. These numbers xi, they're called the shape parameters, and there's this many of them in each tetrahedron. So for example, if n is 2, if you want to make an SL2 connection, you just have to put one number in each tetrahedron. So this construction has been studied a lot. So for n equals 2, it's kind of a classical story, first developed by Bill Thurston. And then more recently for all n, there's work of Thematic, Abelianization, and Gruffelidis, Dylan Thurston, Gerner, and Digger. Now this is kind of, at least for me, this is kind of a weird thing if you think about it, because, of course, the tetrahedron, literally the tetrahedron is just contractible, right? There's no, there are no closed cycles about which to have a monodromy. So the statement that flat connections on this three-manifold are somehow described by local parameters that live inside of each tetrahedron is a little bit strange. And one of the things that one of the outcomes of the work that I'm going to review is, I think, a sort of nice way of understanding why these parameters are there. So these numbers they're not arbitrary numbers, but they're required to obey some algebraic equations. We'll also understand these algebraic equations as we go. Now there's one case where the shape parameters actually do have a geometric meaning, the case that Thurston first studied. And that's the case where you study a hyperbolic manifold, so specifically for SL2, or actually PSL2, but it doesn't make a big difference. And in that case, if you have a hyperbolic manifold and you chop it up into tetrahedra, you just get a bunch of ideal tetrahedra in the hyperbolic upper half space. And each ideal tetrahedron is just determined by, up to the SL2C isometries of hyperbolic upper half space, is just determined by the cross ratio of its four vertices. You can put them at 0, 1, z, and infinity, then this z is the modulus. So just in that case, there's a very clear understanding of what you're doing. You're taking a hyperbolic manifold, cut it up into tetrahedra. Each tetrahedron has a parameter. But for more general connections, been a little bit mysterious. What's the meaning of these parameters? And then the remarkable thing, though, is that these parameters are very convenient. They're very convenient parameters for understanding the Chern-Simons topological field theory. So in particular, if you just want to compute the Chern-Simons invariant, it has this rather beautiful formula which says it's just the sum of the dilogarithms of these parameters. So in particular, the Chern-Simons invariant for these connections always comes to you as the exponential of the sum of dilogarithms of a bunch of algebraic numbers. That's a structure that's not at all obvious when you first write down the formula for the Chern-Simons invariant. Okay. Yeah, so one of the aims of this talk is to explain a sort of alternative geometric picture of these xi, which hopefully makes it obvious why they're there, and also why there's this dilogarithmic formula. And so the spoiler is that we're going to reduce everything to GL1 Chern-Simons, and then in the GL1 Chern-Simons theory, these parameters will be just literally the holonomies of some GL1 connection. Okay, so now let me move to the GL1 theory. So we're going to have an equivalence between the GLN Chern-Simons and a GL1 Chern-Simons. I have to tell you about this GL1 Chern-Simons. It's not quite exactly the conventional GL1 Chern-Simons. It's going to have two extra kinds of defects stuck in. So if I wanted to describe it in this topological field theory language, I would say it's going to be a functor from a slightly fancy Lordism category. We're going to take spin manifolds again. Now I'll call them M twiddle. But these spin manifolds, instead of just carrying GL1C connections, are going to carry GL1C connections plus some extra defects. So here's what a typical morphism in that category might look like. So first, there's this codimension 2 defect. This one plays a rather technical role, but I have to describe it first. And it's not just a line, but it carries a little bit of additional framing structure. So around the place where this defect sits on its linking circle, you have to put 3 mark points. In Chern-Simons theory, we're used to the idea of a framing where you have to put 1 mark point. Here, you have to put something a little different. You have to put 3 mark points, and you have to put little arrows going one way or the other. And so the effect of this defect ultimately is sort of almost trivial, but on the other hand, nothing's right unless you have it. It just contributes a cube root of unity every time the framing winds around. So if you have a closed loop where these 3 points wind around, so they exchange with each other, sort of 2 pi over 3 rotation, then this thing is going to contribute a cube root of unity to the expectation value. And then the second kind of defect is rather more interesting. So this is a codimension 3 defect. So in a 3 manifold, this thing would sit at a point. And the idea is that this point is actually going to be a singularity of the manifold structure of M twiddle. So this theory doesn't quite live on manifolds. It lives on manifolds with occasional little singularities stuck in. And the way you detect that they're singularities is you look at the link of the point. So you imagine sort of drilling out a tiny neighborhood of that point. Now, had it been an ordinary manifold, when you drill out a tiny neighborhood, you always get a 2-sphere. Here, this point is a singularity, and so you don't get a 2-sphere, you get rather a 2 torus. Okay, so we're going to allow singularities where the manifold locally looks like kind of a cone on a 2 torus. And this 2 torus linking the singularity has to receive 4 of these line defects. And now our GL1C connection is supposed to be a little bit singular at these places. So it's going to have holonomies around the 2 cycles of the 2 torus. And the holonomies have to obey a kind of funny-looking constraint, which is, at first you should ignore these plus and minus. The constraint is that the holonomy here, xa, plus the holonomy here, plus or minus the holonomy here, is equal to 1. So these are 2 elements of C star. We're looking at the holonomy of a GL1 connection. So these are 2 numbers in C star, but this is not a multiplicative relation. It's an additive relation. The holonomy here plus the holonomy here equals 1. Okay, so that's our other kind of defect. GL1C theory. Okay, and now I'll start telling you how the topological field theory is actually formulated. So first I have to tell you what it assigns to a surface. And for a surface, well, for just a bare surface, it assigns just the usual line of the GL1 spin Chern-Simons. For the surface with defects impinging on it, it'll assign the line of the GL1C Chern-Simons tensored with an extra kind of universal line for each defect. It depends only on this framing data. Now, the really interesting thing is what do we do with the codimension 3 defects? So at the codimension 3 defects, we've created a little torus boundary. So imagine drilling out a tiny neighborhood of that defect. If we're going to define a modified version of GL1 Chern-Simons, what do I have to do? Well, in order to compute correlation functions, vacuum expectation values with this defect inserted, I have to give you a little element of the Hilbert space on the boundary. In order to make the whole correlation function well-defined, I have to give you a little state on each of these boundaries. Okay, so concretely, I have to give you an element of this Chern-Simons line. Now, that at first might sound hard. You know, the Chern-Simons theory is a non-trivial theory, so how can it have a totally canonical element of its line? But it turns out that there actually is a candidate. So it's given essentially by this formula. So the exponential of the Rogers dilogarithm as a function of the holonomy around this loop. Again, there are strict signs, plus and minus, so some slight variant of the Rogers dilogarithm. Well, what does it mean to say that this is an element of that Chern-Simons line? When you first say this, when you first see this formula, it has kind of two problems on its face. So one problem is that the right side isn't really a function, right? To write the dilogarithm as a function of this element of C star, well, the dilogarithm is a multi-valued function. So in order to even make sense of this, I have to give you a branch of the dilogarithm function. Then on the other side, there's also a problem because this is supposed to be an element of the Chern-Simons line. It's not supposed to be an actual function. In order to turn it into an actual function, you'd have to trivialize the structure. You'd have to choose a trivialization of the bundle underlying this flat GL1C connection. Okay, so the equation has kind of problems on both sides. And the good news is that these problems exactly cancel each other out. So on both sides, in order to solve the problem, what I have to do is I have to choose logarithms of these holonomies, xa and xp. So on the right side, to pick a branch of the Rogers dialog of z, I have to give a choice of log z and a choice of log of 1 minus z. That's log of xa and xp. Then once you make that choice, of course, the Rogers dialogarithm actually depends on which branches you chose. And the cool thing is that dependence is actually exactly what you need, because on the left side, you have to make a choice of a trivialization of the bundle. Trivializing the bundle exactly means specifying logs of xa and xp. And so in Chern-Simons theory, there's the WW cocycle that tells you how your trivialization of the Chern-Simons line bundle depends on the choice of these logs. And that exactly matches the transformation law of the Rogers dialog. So long story short, the dilogarithm function actually is a canonical, well-defined element of the line in Chern-Simons theory, but in a somewhat non-trivial way. I essentially couldn't have written any other function. So the dialog is somehow uniquely suited to make everything gauge invariant. So that's kind of a fun interpretation of the dilogarithm function. If you can't remember, as I couldn't before starting this project, what the dilogarithm function is, but on the other hand, you know everything about spin Chern-Simons theory, then this is how you can remember it. It is, you take the space of flat C-star connections on the torus, that's just C-star squared. You you look inside there, you look at this locus, so that's some kind of Lagrangian submanifold inside the moduli of flat GL1C connections. Then you look at the spin Chern-Simons line bundle, and there's a unique flat section up to overall normalization. That's the dilogarithm. So that's my new definition of the dilogarithm. And then various properties of the dilogarithm you can sort of reinterpret in this way. So for example, the dilogarithm famously obeys a 5-term identity. And the sort of 3-manifold way of understanding this 5-term identity is to look at the 3-manifold, which is just the 3-sphere minus this link. So I just made a sort of chain of 5 circles here. So now the non-trivial thing, which you can check, is that there exists flat GL1 connections on this manifold. There exist flat GL1C connections on this manifold, which obey this condition at all 5 of these torus boundaries. And so if you evaluate the Chern-Simons theory on one of those flat connections, it produces for you an element in the tensor product of these 5 lines. And that element is kind of the abstract version of this dilogarithm identity. So just from the existence of that element, you can deduce the 5-term identity for the dilogarithm up to a constant. Okay. Okay, so I spent a lot of time now telling you about this kind of bizarre-sounding modified version of Chern-Simons theory, where I introduced this slightly ad hoc looking defect. So maybe it's useful to say that these defects have actually appeared before. This being the anniversary of the topological string, it's a good time to explain that origin. So let's think for a minute about the open topological A model. So up till now, I was talking about this manifold M twiddle just as a totally abstract 3-manifold. But suppose that it's not just an abstract 3-manifold. Suppose that it's sitting as a Lagrangian submanifold inside of a Calabi-Yau threefold. So then, a very natural thing to do is to study the open topological string on our Calabi-Yau threefold with just one D-brane wrapped on this Lagrangian submanifold. So then, as Witten famously explained, the target space physics of the A model topological string, the open string field theory that lives on this M twiddle, is, well, it's not quite just GL1C Chern-Simons. It's GL1C Chern-Simons theory plus something else. And the correction is supposed to exactly come from holomorphic curves inside of Y, whose boundary is on M twiddle. So that's this little disk here. So there's a special case of this which gets used a lot, which is the case of a cotangent bundle. In the case of a cotangent bundle, you just literally get Chern-Simons. If you take a cotangent bundle and you put your brain on the 0 section of the cotangent bundle, then Witten says you just literally get Chern-Simons theory on the nose. But in general, if it's not a cotangent bundle, if you have these extra corrections from holomorphic disks, if you have holomorphic curves ending on your Lagrangian, then you don't just get Chern-Simons, you get Chern-Simons plus something else. What is that something else? Well, in the very simplest case, in the case of just a single isolated holomorphic disk, then it was worked out by Oguri and Vafa what the correction is. And the correction is just, you're supposed to take the Chern-Simons action and add to it the dilogarithm, I guess it should be 1 over 2 pi I times the dilogarithm of x, whereby x means the holonomy of the GL1C connection around the boundary of this holomorphic disk. So that's exactly the added term that we're writing down. So this kind of ad hoc looking defect that I introduced earlier in this talk is maybe not so terribly unnatural. It would appear kind of automatically if we thought of M twiddle as living inside of a Calabi-Yau. We would automatically get this kind of deformed Chern-Simons. Now, as a matter of kind of technical convenience in setting up a topological field theory, we did one extra thing, which is I described these boundaries as codimension 3. What that means is every time I see one of these loops, I'm actually crushing it to a point and making a singularity of the manifold. That's not a big deal. Okay. Okay, so far I've sort of reviewed for you the ordinary GLN classical Chern-Simons, and then I've defined for you, or sketched the definition anyway, of a modified version of the GL1 Chern-Simons, GL1 Chern-Simons plus these kinds of extra defects. Okay, so now, how are these two theories related? So I said that there's some kind of equivalence between them. What I precisely mean by that in the topological field theory language is that there's another category here which maps to both of them in such a way that this diagram commutes. So we start with this category of Abelianized connections, which I'm going to define for you momentarily. And then we have two ways of going around this diagram. Given an Abelianized connection, we can either take the GL1 connection part of it and then apply the topological field theory to that, or we can take the GLN part of it and apply the topological field theory to that. So there's two different ways of going around this diagram. You get two different functors from Abelianization to lines, and the statement is that those two are naturally isomorphic. That's the fancy way of saying it. So now I have to tell you a little bit about what are the objects here? What is this new category? So the objects and morphisms in this new category are what we call Abelianized connections. And what is that? It means, well, we have a GLNC connection just like before, but we also have a kind of partial gauge fixing of it. And this partial gauge fixing is going to make it look as Abelian as possible, or as simple as possible. That will mean as Abelian as possible. So what does that mean? It means we try to find a gauge in which the parallel transports are, well, the very best thing would be to have them be diagonal. You pretty quickly see that that's hopeless. If you have a sort of random connection, it's hopeless to make it diagonal everywhere. The next thing you might try is to make it not diagonal, but sort of permutation diagonal. And this is what you actually can do over, in some sense, most of a manifold. So in the bulk of our manifold, the parallel transports, we're going to write them as permutation diagonal matrices. And then, so that means that the parallel transport is given by some matrix like this. And so if you have a permutation diagonal matrix like that, of course, it's just the same as giving a GL1 connection over some covering. So like here we're mapping sheet 1 to sheet 2 with coefficient A. Here we're mapping sheet 2 to sheet 3 with coefficient B. And here we're mapping sheet 1 to sheet 3 coefficient C. So having a kind of permutation diagonal connection is literally the same as having a GL1 connection over the cover. Now usually, if you think about it for a minute, usually you can't do that globally on a manifold. So if you imagine having like a once punctured torus, then you have two monodromies. There's no way you could simultaneously diagonalize those two monodromies. Concerned about that. So instead of diagonalizing the connection everywhere, what you can do instead is introduce a little stratification called a spectral network. And so the way the stratification is going to work is that in the bulk the thing is diagonal, permutation diagonal. Then there's some codimension 1 strata called the walls, where the gauge is allowed to jump, but it jumps not arbitrarily, but just by a unipotent matrix. Then on codimension 2 strata, we have to allow a slightly worse singularity around which M total is branched. I don't like where this is headed. So on the codimension 3 strata, which are points, we have to allow a more elaborate kind of singularity, whose linking sphere looks like this. So this is a place which is not a singularity of our original manifold or of our original connection, but in this in this covering, there will be a codimension 3 singularity, the kind of singularity that I introduced before. Okay, so now let me explain how you use this kind of partial gauge fixing to actually compute the Chern-Simons invariant. Well, it's not very hard. So there's the Chern-Simons action. And now we're writing this connection in a gauge where it's diagonal almost everywhere. So if you have a diagonal, if A is diagonal, then of course the trace of this diagonal matrix is just the sum of its diagonal entries. And so you just wind up summing over the n sheets of this covering. The integral of this term is 0 for non-abelian connection. You just wind up with this, which is the abelian GL1 Chern-Simons. So for essentially, for a completely trivial reason, if you can write the connection, if you can write your connection in an abelian gauge, then of course the Chern-Simons action just reduces to the abelian Chern-Simons. Now, of course, all the subtlety comes from the fact that you can't actually do that everywhere. You can't literally write the connection as abelian everywhere. Nevertheless, we've set it up in such a way that the jumps of the gauge in codimension 1, they come just from unipotent matrices, and those actually don't contribute in the Chern-Simons action. So all you're left with is a contribution from these lower strata, these codimension 2 and codimension 3 strata, and that's what produces the defects that I described in the GL1C, the modified GL1C. Okay, so let me describe a few examples of how this story works. So the basic case, let's go to a 2-manifold for a minute. Let's consider a triangulated 2-manifold, and let's put punctures at all the vertices, so it's an ideal triangulation. So in that case, you can draw a kind of simple example of this structure of a spectral network. I'll just put branch points in the middle of each a branch point in the middle of each triangle, and walls connecting it to the vertices. And then, so that's for SL2, and for SL3, there's a slightly fancier way of making a threefold cover, and so on. Sorry, I'm making a spectral network together with a threefold cover. Now, as it turns out, with this picture of a spectral network, if you have a generic flat connection over your 2-manifold, it can be abelianized, meaning you can make it diagonal here, diagonal here, diagonal here, with unipotent jumps across these walls. It can be done, and moreover, it can be done almost uniquely. There's essentially up to some finite choice. It's unique up to a finite choice. I mean, there's only finitely many ways to do it. And so that literally gives you a translation between the sort of difficult thing, the GLN connections, and the simple thing, the GL1 connections. In fact, the holonomies of the GL1 connections give you coordinates, so-called cluster coordinates, which determine your original connection. Okay, so, and that story, that's a sort of older story which was used by Bach and Goncharov in studying these moduli spaces, which got used in the study of theories of class S, my old work with Gato and more. So now there's a kind of 3-manifold analog to that. So now suppose you're given a triangulated 3-manifold, then once again there's a kind of natural way of making a double cover over it. So this is directly relevant to the SL2 story. So there's a natural double cover over it in a spectral network that you can draw there. This double cover has been considered before in the theories of class R. Chakotay, Cordova, and Vampa introduced this thing, and they called it essentially the kind of Seiberg-Witten 3-manifold. So here we're using the same 3-manifold. And here you can make a picture of you can make a spectral network. So now the walls are 2-dimensional, and they form the so-called dual spine of the triangulation. So you look at this picture of the walls, its intersection with the faces of the triangulation is what we had before, and it's extended into the interior. In the middle, there's some terrible point where all the walls meet, everything comes together, and that's this codimension 3 defect. So now we're in a position to understand the thing I described early in the talk, the statement that there's a construction of flat connections using, there's a construction of flat SL2C connections on M using one parameter in each tetrahedron, obeying some equations. So I described that parameter as being somehow mysterious. From this point of view, it's somehow easy to understand. Namely, here's how we make the connection. We first make a GL1C connection over the cover. Now here, in this picture, downstairs on M, the tetrahedron is just simply connected, but upstairs it's not simply connected. Upstairs there's a little loop. And Xi is just the holonomy of our GL1C connection around that loop. And then when we build, so it turns out in this case that this process of going back and forth between the GL1 connection and the GLN connection is unique. So once we have the GL1 connection upstairs, then you just build the unique corresponding connection over M. Okay, so now let me explain where these dilogarithm formulas come from this point of view. So I told you that there's supposed to be an equivalence between Chern-Simons theories, the Chern-Simons theory downstairs on this triangulated 3 manifold, and the Chern-Simons theory upstairs on its cover. So what that means is if I want to compute the Chern-Simons invariant downstairs, I can compute it in this GL1 theory with defects upstairs. Well, okay, so how do I compute in the GL1 Chern-Simons theory? So in general, that doesn't sound so easy. The GL1 Chern-Simons theory is not completely trivial. On the other hand, in this case, it turns out that the line bundle underlying this GL1C connection on the cover, it does turn out to be globally trivial. So what we do, we just choose a trivialization of that line bundle. Then once you do that, then the GL1C theory really is trivial, right? Because the action is literally the exponential integral of A wedge F. You take a flat connection, that integral is just 0, and so the bulk just contributes 1. And so the whole answer gets localized to the defects. Most of the guts of the answer is in these codimension 3 defects, which contribute these dilogarithms. And then there is one extra subtlety, which is responsible for about 2 years of the length of this project, which is that you have to include these codimension 2 defects, and the codimension 2 defects can contribute third roots of unity. And so this is the sort of Abelianization explanation of the dilogarithm formulas that I told you before in the case of SL2C. Actually, it's a very slight improvement of those formulas coming from these third roots of unity. Okay. Okay, so far, what have I told you? So far, I told you that anytime we have a connection which is Abelianized, meaning we have a way of putting it in this sort of very structured kind of gauge, which is almost diagonal and jumps in these very specific ways, that then there's a corresponding equivalence of Chern-Simons theories. Now, that statement, in order for that statement to be really interesting, there should be some natural way of getting these Abelianized connections. So, I want to just briefly explain how you get kind of natural examples of this structure. Let me start in the 2-dimensional case. So suppose you have a 2-manifold which is actually a Riemann surface with some punctures on it. So then you can consider a Schrödinger equation, let's say a meromorphic Schrödinger equation on that surface. So that's locally an equation that just looks like the usual Schrödinger equation, e by dz squared minus some potential equals 0. Or you could also consider a higher order analog of that. So here's a third order equation, T2. So those equations, if you just study the evolution of the solutions of those equations around the surface, that gives you a flat connection over this surface. And I want to say that these flat connections that arise in this way, are actually kind of automatically Abelianized. The structure of Abelianization is completely natural for these kind of equations, for these kind of flat connections. So why is that? So let me tell it to you for SL2. You think about how you actually go about solving these equations. And so one of the standard ways of solving such an equation is to try to solve it by the WKB method. What's the WKB method? Well, you write down a solution like you try to write down a solution like this. Exponential of some integral, and the integrand of that integral is given by the first term is the square root of the potential, and then there are higher order terms in the integrand. They're just determined by recursively plugging back into the equation. So what does that mean? What's the kind of geometric structure of that? Well, the geometric structure of that is to specify a solution, I have to choose a square root of this potential. That means choosing one of the 2 points of this double cover. And so I'm getting solutions which naturally live over this double cover. Actual solutions which live over this double cover. Now those local solutions, to actually construct the solutions, you have to do a kind of Borel resummation. And so the result of that is that those local solutions don't exist everywhere in the manifold. They only exist in some domains of the manifold, separated by these so-called Stokes curves. And these Stokes curves exactly form the structure of a spectral network that I was describing before. And when you cross the Stokes curves, there's this WKB connection formula that tells you how the solutions in one domain change from the solutions in another domain. And they change exactly by a unipotent matrix. So it's exactly the structure that we introduced before. So this is the picture for rank 2 for like a Schrodinger type equation. This is an example of a picture for rank 3. As you can see, these networks get a little hairy. Yeah, so the structure is exactly the structure of this Abelianization. And so for SL2, it's equivalent to the thing I told you about ideal triangulations. In higher rank, it's not captured by ideal triangulations. I don't think it's really known what's the corresponding combinatorial description. So to connect this with quantum field theory a little bit, okay, let's just say, I'm short on time. In quantum field theories of class S, flat connections kind of canonically arise. They arise because you study a surface defect that has some parameter. Then it automatically gets a flat connection in its vacuum bundle. And that flat connection comes automatically with this kind of Abelianization. It gets Abelianized to a GL1 connection over the Seibert-Witten curve, essentially just by going from the UV description to the IR description. So this notion of Abelianization arises automatically in these theories of class S, Abelianization over 2 manifolds. So what we would really like is to have an analogous story for 3 manifolds having to do with quantum field theories of class R. So something having to do with the physics of surface defects in theories of class R. That's where I would hope that natural sort of physical use of this construction is going to be. And that might give a source of kind of interesting geometric examples of the kind that I was showing you for WKB over 2 manifolds. So right now we don't have that, so, okay, so what have I told you? So I just told you that there's some relation between 2 versions of classical complex Chern-Simons. On the one hand, GLN theory here, and on the other hand, GL1 theory here. And okay, it gives you a new way of thinking about some aspects of the GLN theory, and it still remains to find the sort of, the really, I would say, killer application